Hello everyone, this is Shravani. Today I'm going to summarize an IEEE paper which mainly discusses about the analysis of the dimensionality issues in house price forecasting. House price fluctuations in the real estate market occur due to the effects of other variables that are correlated to housing prices. For instance, the size, location, number of bedrooms, schools, shopping malls, and availability of elevator for the apartments, and many more correlated and relevant features will contribute added value to your house. However, the main factor that determines the value of a house is the demand. The problem of housing price forecasting remains a common issue across the globe. Stakeholders are still looking for a reliable method for determining the probable selling price of a property. The experiment results in the paper demonstrate that there is a substantial difference between using and not using a feature selection in terms of performance in predicting houses prices. The main agenda of this presentation is first we'll see about what is a feature selection and what are the basic feature selection techniques and what is a PCA and what is the difference between PCA and PSO. PSO stands for particle swarm optimization, and the basic inspiration behind this particle swarm optimization algorithm. So for so first let's see what is a feature selection and why it is used. Feature selection process is one of the main components of a feature engineering process. This is how a predictive model is developed by reducing the number of input variables. Feature selection techniques are employed to reduce the number of input variables by eliminating redundant or irrelevant features. It then narrows the set of features to those most relevant to the machine learning model. There are different types of feature selection techniques. There are two categories, which is supervised and unsupervised. Feature selection model. First, if we come to supervised model, supervised feature selection refers to the method which uses the output class for which is a target variable for the feature selection. That means they use the target variables to identify the variables which can increase the efficiency of the model. So, when in contrast, when it comes to unsupervised feature selection, the goal of the feature selection for unsupervised learning is to find the smallest feature subset that best uncovers the interesting natural groupings from data according to the chosen criteria. So, there may exist multiple redundant subset solutions. First, let's see about what is filtering. Filtering methods are generally used as a pre-processing step. The selection of features is independent of any machine learning algorithms. Instead, features are selected on the basis of their scores in various statistical tests for their correlation with the outcoming variable. Whereas in wrapping methods, we try to use a subset of features and train a model using them. Based on the inferences that we draw from the previous model, we decide to add or remove the features from your subset. The problem is essentially reduced to a search problem. So these methods are usually computationally very expensive. So under supervised feature selection, there is an algorithm, famous algorithm called PCA, which stands for principal component analysis. A PCA is a statistical method normally used for data analysis and is a very useful method of feature selection. It is applied to transform raw features into principal features so that the features are more clearly visible and their importance is visualized. This technique has been used for the last few years in different domains. In this technique, the features are selected based on eigenvalues. The features with the higher eigenvalues are selected and the features with the lower eigenvalues are ignored. So this method of feature selection is not an optimal mode due to the probability of losing some important features. So this is an optimization problem. Here comes the PSO, which is a particle swarm optimization. So PSO is the best method for solving this optimization problem. In PCA, first we'll have an input feature vector. You Using that feature vector, we calculate the mean, and from that mean we calculate the deviation, and using the deviation we calculate the covariance, and based on this we determine the eigenvalues and eigenvectors, and which are having the higher eigenvalues are considered, and the lower eigenvalues are ignored. So finally we'll get a principal components. So when it comes to PSO, so the basic inspiration behind this algorithm is that the particle swarm optimization was proposed by Kennedy and Eberhart in 1995. So, as mentioned in the original paper, sociobiologists believe a school of fish or a flock of birds that moves in a group can profit from the experience of all other members. So, in other words, while a bird flies and searches randomly for food, for instance, all birds in the flock can share their discovery and help the entire flock get the best hunt. While we can simulate the movement of a block of birds, we can also imagine each bird is to help us find the optimal solution in a high dimensional solution space, and the best solution found by the flock is the best solution in the space. So this figure illustrates the flow of PSO for feature selection. So the first step is initialize an array of particles with random positions and velocities on d dimensions. Next is evaluate the desired minimization function in d variables. Next, we'll compare evaluation with particles' previous best value, and if the current value is less than the previous best value, we will update the p best to the current value. So next step is to compare with group's previous value. If the current value is less than the previous group's best value, then groups update the group's best value with the particles array index. So next step is to update the position and the positions of the particle. So once the criterion is met, global best and the present value are returned. Otherwise, the previous steps are looped through. So now let's see how the PSO works in a search space. So first, a group of particles which are the potential solutions for the global minimum in the search space. There is only a global minimum in this search, which is this X mark as shown in this figure. None of the particles knows where the global minimum is located, but all the particles have a fitness values evaluated by the fitness function to be optimized. So here in this diagram, if you see, these are all the individual particles which are randomly initialized. So the particles have already been randomly distributed in the search space. So their velocity must then be initialized, defined by its speed in each direction. The velocity vector will once again be randomized. Over the iterations in the search space, the speed of each particle is stochastically accelerated towards its previous best position, which is the personal best, and the best solution of the group, which is the global best. Concretely, at each iteration, each particle is updated according to its velocity. This velocity is subject to inertia and is governed by the two best values found so far. So, the first value is the best personal solution the particle has found so far, and the second one is the best global solution that the swarm, that means the group of the particles, has found so far. So, each particle has in memory its best personal solution and the best global solution. So if we see this diagram, the group of the particles where the best position of each particle is marked in with a black dot to distinguish from their current position, which is set in the blue. So here the star, if you see, it denotes the global best position. This is in the this is after the first iteration. So after fifth iteration, note that the position of the global best in the previous first iteration, the global best is here, whereas after fifth iteration the global best has shifted to here, so which is almost closer to the final solution, which is the global minimum. So after, if we keep running the algorithm continuously, and after 19th iteration we can see that we are already very close to the optimal. This animation shows how we find the optimal solution as the algorithm progressed. So this resembles the movement of a flock of birds. In this particular example, the global minimum we found by exhaustive search is at the coordinate 3.182 and 3.131, and the one we found by PSO algorithm is at 3.185 and 3.130. So after using this PSO algorithm, some of our features which are available in the prediction of house prices will get reduced. So those reduced features are then used to train the models and test the model and get the accuracy. So it is the model performance. It is before applying PSO. If we see here, we have used four classifiers, which is random forest, KNN, and all. And the performance matrix is correlation coefficient, root mean square error. If we see RF is 88 percentile, the performance metrics we have seen, and after applying PSO, the performance metrics, if you see, this got increased. It is 88, it got increased to 96%. So it is very clear that there is a significant increase in terms of performance metrics for all four classifiers when features are selected based on the PSO. Similarly, the performance metrics used in the regression based model at the correlation coefficient MAE RMSE also got increased. So in this study, it was mainly aimed to address the issue of dimensionality in the Ames house dataset and to use machine learning modeling to forecast house prices. Hence, we explored the effect of embedding the PSO technique for selecting important and relevant features that would strongly impact the house price forecasting model. And it was also explored that the use of classification and regression tasks in building the house price forecasting models. The results showed that a random forest model is the most accurate forecaster among all the algorithms for both the classification and regression tasks. So, the future directions of this study will include exploring the extensibility of house pricing models by experimenting with clustering or hybrid techniques.